Hello and welcome. Today we're going to be doing error approximation estimation using Taylor's inequality. Okay, so what is Taylor's inequality? So the idea is this. We want to make some approximation. And we can call it Sn of x, which is going to be the sum starting from n equals 0 up to capital N of Cn x minus a to the n, right? Where Cn are the Taylor polynomial coefficients. Like that. Okay. All right, and of course we want to know how well this Sn of x, how close it is to just the actual Taylor series. We'll just write it as f of x, where f of x is the same sum at start, but we go all the way up forever. Like that. Okay, so this is where Taylor's inequality comes in. So the inequality is pretty straightforward. It says that the error S capital N of x minus f of x is less than or equal to some number big M all over capital N plus 1 factorial of x minus a to the n plus 1. This is bounded on the domain x minus a is less than or equal to some d value, and this is of course given. All right, and that m, I can write it as the maximum of x on the set x minus a less than d, less than or equal to d, of this function of the n plus 1th derivative of x in absolute value. Okay, all right, so that's a lot to say, but essentially the idea is basically once we find the value here, once we find this value here, then all of a sudden the error, I know what size the error is. I know it could be no bigger than the size of the underlying quantity there. So let's actually just use this procedure a few times to see how it works. Okay. So the standard thing is to, of course, you have to have a set of givens. Okay, you have f, and then you have some n approximation. All right, and then you have to have some domain of interest. And that, of course, is going to be, and okay, I should also mention that the n approximation has to have some expansion. We were going to do a particular approximation of a Taylor series with x equals a domain of interest. In this case, that domain of interest is just going to be x minus a is less than or equal to d. Okay, so that's some domain of interest. We have to have all of these things given. Okay, so of course our approximation, we want to call it Sn of x, is going to be, of course, f evaluated at a plus f prime evaluated at a over 1 of x minus a 1 plus dot 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 all the way up to f capital N evaluated at a over n capital N factorial of x minus a to the n power. All right, so this is some polynomial approximation. We want to know how good this is at approximating the actual f function. All right, so let's actually get started, and we're just going to do some examples. So the first example we're going to do is we're going to start with, so this is our first example, we're going to start with f of x is equal to cosine of x, okay? And what we're going to look for is the quadratic approximation. So this is going to be n is equal to 2, all right? And the domain let's look at this domain. I want to find out the domain we're going to have a is equal to 0, and we're going to have x is less than or equal to pi over 4. All right, so we're looking at this domain here from 0 up to pi over 4, and then, of course, back to negative pi over 4. So I want to know what the function's doing there. So it might be good to just give this a graph here for a second. We know that cosine is going to do one of these things here. That's cosine of x right there. So I want to find out what S2 of x is. That's the first thing we got to do. All right, so we might as well just find that. So first off, we find f of 0, which is going to be cosine of 0, which is equal to 1. All right, f prime of x, of course, is going to be sine of x. We evaluate that at 0, and of course we get 0. All right, and then we have f double prime of x. And that's going to be, oh, sorry, that's negative sine. My bad there. Right, and then finally we're going to take the derivative of negative sine and get negative cosine of x. We're going to evaluate that at 0, and we're going to get 1 there as well. All right, so all of this put together allows us to write out what S capital N is. It's going to be 1 minus 1 over 2 factorial. Hold on one second. I'm going to back up just a little bit. Plus, I'm going to say this is going to be 0 times x to the first power, right? Because what we're doing here is I'm taking, that's my coefficient there, plus negative 1 all over 2 factorial of x squared. Right, so let me just write this a little bit more concisely as we're putting this together. This is 1 minus 1/2 x squared. And I want to know how close is Sn to cosine of x on this domain right here. All right, so on this domain, I want to know. So if we look at this function right here, let's say if I were to just draw it there, if I were to make a graph, it would probably look a little like that. It's going to be a downward shaped parabola, but it's not going to be a perfect fit to cosine. But it should be there. Who knows exactly where? All right, so without a calculator or any kind of technology tool, we can come up with a bound for this using Taylor's inequality. So what we first need to do is actually calculate, again, the bound. We had written it before. Let me just highlight this again. It's going to be here in red. It's right here, this red thing here. And what we really need to calculate is this derivative of the n+1th derivative. So let's now go back and calculate this up. Okay. So the point here is, though, is that the n+1th derivative has to be evaluated. We want to find the maximum on the entire domain here, and I'll underline that really heavily there. Okay. So that's really a lot of the work, and the rest is just assembly, putting this number together and finding out how to make this as big as possible. All right. So let's go back to our original calculation. So again, what we need to calculate is this m value, which is going to be the maximum of x on this domain, x all the way up to pi over 4 and negative pi over 4, of the absolute value of the, in this case, because n is equal to 2, that means n plus 1 is equal to 3. So we have to take the third derivative, triple prime, of x in absolute value. All right, so the derivative then, f triple prime of x, of course, is going to be positive sine of x. All right, so there's our derivative, and I want to find that bound. So that means that m, my m number, is going to be, I have to find it has to be the maximum of x on this interval, negative pi over 4 to pi over 4, of the absolute value of sine of x. Okay. All right, so it should be pretty clear that this has to be the absolute value of sine at pi over 4. Okay, and that of course is going to be the square root of 2 over 2. Check your your tables there. This is approximately equal to 0.707. Okay, I checked that on the calculator ahead of time. All right, so that's what the value of our m is. So probably worthwhile to just circle that, and now we're ready to actually compute the bound. All right, so the error, which is equal to s2 of x minus cosine of x, is less than or equal to square root of 2 over 2. That's my m value right there, okay? All over, and again, n plus 1 is equal to 3, so it's going to be 3 factorial. Then I have to multiply by x, and in this case a is 0, so we can just go absolute value of x to the third power. All right, so I want to know how big the error could get on this, so the question then is how big can this be? Well, of course, it's the biggest at x is equal to pi over 4. Okay, so what I'm going to do is actually put that in. So this whole thing then becomes square root of 2. 3 factorial, that's actually equal to 6. So we can write that as 2 times 6, which is 12, times pi over 4 to the third power. I'll let you compute what that value is. If you use a calculator, you can figure that out and figure out what that number is. But what's important about it is that that is actually a good estimate then of how far off the quadratic approximation is to cosine. Why this is important is because you may want to, sometimes when you're doing mathematical analysis, you may want to take a complicated function like cosine and approximate it by a simple quadratic function. And that might be good for your purposes, but you want to know how far off it could possibly be. And the Taylor inequality gives you an estimate of that error. Okay. All right, so now let's go to another problem. Right, so the problem we're going to talk about today, we're going to do yet another one involving a function I think we're all fairly familiar with, which is f of x is equal to e to the negative x. Okay, all right. And what I'm going to look at is s2 of x, which is again another quadratic approximation. It's a quadratic approximation. And we're going to take a is equal to 0. And what I want to know is, I'm going to look on the interval, the domain of x is absolute value less than 1. All right, so I'm going to just graph this. We know that e to the x has this sort of look to it, like this. So that's e to the negative x right there. And I'm going to go from negative 1 up to 1. All right, so of course right here at this point, that is e to the negative 1. And here this is e to the 1 right there. Okay, so the question then is, if now I want to find the quadratic approximation. So I need to find S2. That's the first thing I need to do. So let's do that. This is going to be e to the negative 0 minus e to the negative 0 over 1 factorial, okay, plus e to the negative 0 over 2 factorial times x squared. Oh, you know what? I forgot my x to the first power. All right, so that's the Taylor approximation. Let me just summarize. This is going to be 1 it's going to be minus x, and then it's going to be plus 1/2 x squared. Right, so this polynomial then is going to approximate in some way how this works. So let's, if I were to draw this line, I don't know, it would be something like this. Who knows exactly what it's doing here? So now let's, sorry, I got to resize here. Okay, we're back in action. So if this is my approximation, S2 of x, I want to know how good it is. And I have actually a specific question I'm going to ask. Does the inequality does the Taylor inequality guarantee an error less than 1/2? So I have a yes or no question I'm trying to answer here. All right, so let's go and figure this out. So I need to actually figure out, again, the same thing. We need to figure out our m, which in this case is going to be the maximum of x on the domain absolute value less than or equal to 1. Okay, so we can take that domain is less than or equal to 1. I shouldn't have written that as just a strictly less than of the maximum of e to the negative x triple prime. Okay, so e to the x triple prime, that's going to be maximum absolute value of x less than or equal to 1. That's going to be negative e. We're going to take the absolute value of e to the negative x. Clearly, this is going to be biggest at e to the 1. So that's going to be, of course, e to the negative 1 in absolute value, which of course just becomes e to the 1. So that's about, 2.71. That's about the m value there. All right, so we've done the heavy lifting in terms of finding out what that maximum derivative is on that domain of interest. So now let's construct our error, which is equal to S2 of x minus e to the negative x in absolute value. This is going to be less than or equal to e to the 1 over, again, we have, of course, capital N plus 1 is equal to 3. So we're going to have 3 factorial, which is equal to 6. So I can just put a 6 down there right now. Okay, and then we're going to multiply by x in absolute value to the 3rd power. Right, I want to get this, I want to figure out, so the question then again is on the domain absolute value of x is less than or equal to 1, is the error within 1/2. All right, so I need to find out if this object, does this get bigger than 1/2 on x's being less than or equal to 1? So that's ultimately the question I have to answer. So of course, x being equal to 1 makes e1 over 6 1 biggest. Okay, so the question then is e to the 1 over 6 times 1 is this. Note that, of course, that is this less than 1/2? And I'll put a question mark there. We want to know that. And then what I want to note for you is that e, which is equal to 2.71 ... is less than 3. Okay, so that means e to the 1 over 6 is actually less than 3 over 6, which is actually equal to 1/2. So check. The answer then, of course, is yes. I've used the error analysis formula here to actually answer a question about whether or not the quadratic approximation, this blue line up here in the graph that I drew, again, that's just approximate. If that graph, if that quadratic approximation stays within a certain error tolerance over the interval -1 to 1 on the x-axis. And the answer in this particular case is yes. We've used the analysis theorem. So the Taylor inequality, of course, it's an approximation theorem, but it can be used to answer really specific questions that are important, of course, in applied mathematics, which is all about approximation of things using rigorous mathematical theories. The most important of these theories, of course, is the Taylor inequality. Taylor inequality shows up in many analyses in physics because it helps us guarantee an error. And that's really important when you're doing a lot of applied math. All right, well, anyway, I hope these two examples help you understand more about how to use the Taylor inequality to answer specific questions about accuracy of approximations. Thank you very much.